connected to DO. So if I want to draw the output voltage from Z1 from 0 to pi, the output voltage will become exactly same as Vs, which is this black. For the second part, which is from pi to 2 pi, the input voltage is negative, therefore D1 becomes off and D2 becomes, or Dm becomes on. I told the reason. The reason is that once D1 becomes off, because of this inductor and this constant current which goes through this load and inductor, if D1 becomes off, this current should continue flowing in some direction. So this current forces Dm to become on. So you understood the reason? So for becoming Dm becoming on is not the voltage. The reason of Dm to become on is the current of the inductor which is flowing and it wants to continue flowing. So this will force Dm to become on. So during this from pi to 2 pi, D1 is off because of the negative voltage which we have, and Dm becomes on. So if I want to draw the output voltage again, I can see that in this condition, Dm becomes off. Means that here is short circuited to this. So how much is the output voltage? Is 0, right? So if I want to draw the output voltage from pi to 2 pi, it will be 0 value. On the other hand, now I want to draw the current waveforms for D1. So I know that when D1 is on, from pi to 2 pi, once D1 is off, the current becomes 0. You see this blue line, from pi to 2 pi, D1 is off. So it's very simple. The current is 0. From 0 to pi, which is D1 is on, Dm is off. So I don't have this branch, and IO is rotating in this loop. It's following this loop. So ID1 becomes equal to IO. So IO was a constant value. So ID1, which is this blue one, blue line, ID1 which exactly becomes like IO. Since IO was a constant current, so ID1 becomes a constant current. And from pi to 2 pi, D1 is off, so its current becomes 0. For Dm, the same thing happens. From 0 to pi, Dm is off, so its current becomes 0. And from pi to 2 pi, again D1 is off, we have this Dm. So the current of Dm, diode N, will become equal to the output current, which is IO. So you can see, from at pi, suddenly the current jumps from 0 to IO and will be a constant value. So this is the current of ID1 will be this blue line, which is 0 to pi, has a positive value, and here is 0, and vice versa is for Dm. Now I want to see how much is the input current. Input current, which is this current which comes from transformer. If again if I consider this one as Is, and you have these two transformers which the direction is the parameters. Now it's asking us to calculate the power factor and THD of the rectifier. Remember from mathematics, I don't know, you should have studied this. So now, from now on, in some of the questions, we need to calculate the Fourier transform. And like the first class, which I told you, please learn how to calculate average and RMS. FFT also becomes necessary for you. And I remember last year exam also we had a question. So please, if you also forget it, because it's not a class for teaching FFT. So you are just using it. If you don't forget it, please go and review and remember. So for Fourier transform, we need to calculate the parameters of A and AN and BN. If you remember, A0, which is our DC parameter of the Fourier transform, which is equal to the DC part of the output current. Now we want to calculate the Fourier transform for IP. So you see, the Fourier transform which you are calculating is for this signal, which is from 0 to pi, has a positive value, and from pi to pi is 0. So we want to calculate, I am telling that A0 is equal to IDC. So IDC is very simple, you can easily calculate. So you calculate the integral from 0 to 2 pi, but from pi to pi, 2 pi is 0. So the integral becomes from 0 to pi. And this IA is a constant value because it's this. So you can easily calculate that A0 becomes to IA over 2. So you have this. You see here the amplitude is IA. For calculating the AN, we need to calculate IPT cosine n omega t d omega t. I am telling you, if you forget about Fourier transform, please go and learn. You need it. So again we calculate the integral from pi to 2 pi. Again the integral becomes 0. So again the integral for AN becomes 0 to pi IA cosine n omega t is part of the equation for Fourier transform. You don't say that. This is not this cosine n omega t is part of the Fourier transform, not part of my signal. So my signal is only IA or IPT, which is a constant value. So IPT is a constant value from 0 to pi, so I put a constant value, IA. Cosine n omega t omega t. So if you calculate the integral for cosine becomes sine or minus sine, and if you calculate the integral from 0 to pi, AN becomes 0. So the same thing goes to BN for Fourier transform. But in BN, you know that for AN we had IPT cosine n omega t d omega t. For BN of Fourier transform, we have IPT sine n omega t. So the same thing. We need to calculate the integral. So again from pi to 2 pi becomes 0. So we need to calculate from 0 to pi. And our signal becomes IA. So this is only calculating the integral. So my final value of the integral will become IA over pi multiplied by cosine 0 minus cosine NP. So now we see different values for n. For example, if I put n equal to 1, okay, so will become cosine pi. Cosine pi is minus 1, and cosine 0 is also 1. So will be 1 minus 1, which the whole thing becomes 2. So you don't be confused. If n is odd number, cosine np becomes minus 1. If you put n as 2, cosine 2 pi is equal to cosine 0, which is 1. So will be cosine an even number like 2, this becomes 0. So the whole thing becomes 0. So Bn becomes 0. So I know that Bn for even numbers of n is 0. And n for odd numbers, Bn for odd numbers of n becomes, here becomes 2. So 2ia over 5. Does any one of you know what is this n in the Fourier transform? What is this n? Do you remember? Harmonic, yes. So this means that, for example, if I am using here as an electrical game. So if n is 1, I'm calculating the signal in fundamental frequency. Okay, the purpose of this Fourier transform is, if I want to make it simpler for you, I can say, assume I have this signal. Whatever it is, this is a square wave signal. But whatever we have in the electrical net, we are doing everything for sinusoidal. So I need to calculate the sinusoidal equivalent or parameters for this signal. So I can say that this signal, for example, is equal to this signal plus, I am telling you as an example, again, you don't say this is wrong, or I am telling you as an example, plus another sinusoidal plus another sinusoidal, which their frequency is different. So I can say that this is my signal in fundamental frequency, which n is equal to 1. This blue line or this red line is my equivalent signal in third harmony, which is n equal to 3, and this blue line is for fifth harmony, which is n equal to 5. So in the Fourier transform, we are trying to calculate the value of the parameters of these three signals, which I have drawn here. So this is the purpose. So once I say that, and okay, I can say that if I have a signal in time domain and I want to calculate this, the Fourier transform of this, I will have an, the parameters an and bn. So here I can say that f is equal to an cosine omega t or cosine n omega t plus bn sine n omega t. So this is the Fourier transform of signal which I have. So you see here, this is the sine or cosine, which is the sinusoidal waveform which we know. So we are transferring or converting this signal, which was a square wave, to a signal which is consisting of 2, 3, 4 or n number of sinusoidal waveforms. So this is the purpose. So here we have calculated Bn, which is in our Fourier transform. So now for the Fourier transform, we can write also like this, that instead of writing an cosine n omega t plus pn sine omega t, you can write this whole thing as cn sine n omega t plus phi n. Okay? So this cn is the whole amplitude of our signal for nth harmony. This is not a one value. For the fundamental is one value, for n equal to 2 is another value, for n equal to 3 is another value. So this is the whole addition of all of these different values. So if you want to calculate Cn, here in this equation, Cn is equal to put an square plus Cn. So if I want to calculate the Cn becomes, if you remember, a and b was 0. So I have Bn becomes the amplitude of our output. Again, for this you can calculate the RMS value, like the way which I have calculated. This is the RMS. So now I have calculated the fundamental, which is I root 2 IA over pi, and I have calculated the RMS of this signal. For the THD, or total harmonic distortion, tomorrow you have the lecture and professor will teach you this equation for the THD. So, which is RMS, IS is the whole RMS of the signal over I1. I1 is the RMS of the fundamental frequency or fundamental signal. So, IS, but again I say IS is the RMS of the whole pi. Because of this, I have calculated the IRMS according to the signal itself. Because I have two ways for calculation of the RMS. If I have the signal and Fourier transform, that I can say is equal to A1 sine omega t plus B1 cosine plus B2 sine all the way. So I can calculate the RMS like this, that is equal to A1, or if I write this, all of this thing as C1 sine omega t plus phi1 plus C2 sine omega t plus phi2. So if I have this thing for the RMS, I can say that F RMS is equal to C1 square to power of 2 plus C2 to power of 2 plus C3 to power of 2 plus till infinity. So this is also one way of calculating the RMS of this current. So since I can say that in this question I have calculated the parameter of Cn, I can calculate C1, C2, C3, C4, C5, C10, C100, C2000. Okay? This is one way which you can do that. But if you want to calculate all of these things, it will become more difficult. Okay? So another way is, instead of doing this, you calculate the RMS, IRMS, from the signal itself. Because in most of the ways, if you calculate by this equation, or you calculate the RMS from the signal itself, the RMS value will become the same. So for us, it is easier to calculate the RMS value of the signal from the signal itself instead of using the Fourier transform. So because of this, I showed you that since I wanted to calculate the THD, I needed the IRMS, which IS is IRMS, and I fundamental. So I have calculated the I fundamental here and IRMS. So now we can calculate the THD by just substituting the values. So you can see that I have substituted the values, and at the end THD is 1.21. So one question. So what is the THD or total harmonic distortion? You know again what is this? Any idea? Do you have, I think you should have this in another courses previously. This is not the first time you want to learn. Okay. Whatever I expect in the electrical engineering is a pure sinusoidal waveform for current and voltage. And the frequency which I expect is 50 Hz or 60 Hz, whatever it is. But in different topologies, like the rectifier which we have, the input current is not a sinusoidal current. So it's a square wave. We want to see how good or how pure sinusoidal is our input current. So for this, we define the parameter as total harmonic distortion. Okay, total harmonic distortion. Another equation for the main equation the parameters and ratings of diode and supply transformer. First, as you can see, we need to, the question is asking us to sketch the voltage and current waveform. So, here I have 4 diodes, and this is my input voltage. Same as every time, this is my input voltage, which is sinusoidal. So, I see from 0 to pi, the input voltage is positive. The input voltage is positive means that Vs, which is connected to this point, is positive and larger than this side. So, since this voltage is positive, V1 becomes on and V4 becomes off. So, the current flows through the load, and in this branch, you see this voltage, which is connected to minus Vs, is the negative value. Therefore, V3 becomes off, V2 becomes on. So I can say from 0 to pi, V1 becomes on, so the current flows to load like this, and then comes to V2 and goes to source. So always we should consider that there should be a current path for the flowing of the current. So D1 on, D2 off, D3 and D4 becomes off. So in this condition, D1 is on. So positive point of source is connected to positive point of load, and D2 is on. So from here, the negative point of load is connected to negative point of source. It means that VO is equal to Vs. So if I want to draw VO, will be this blue line. From pi to pi, the same procedure we follow. Voltage is negative means that here the voltage is negative. In this branch, this voltage, this point is negative. So D1 becomes off, D4 becomes on, and vice versa. Here the voltage is positive, D3 becomes on, D2 becomes off. So the current path will become from here. If you see, from here goes to D3, then goes to load, R, and D4 comes here to transformer, and again. So you understood. So in this case, if you see, you can see that the negative point of load is connected to positive point of load, which is connected to here, is connected to negative point of load. From here is connected to positive. So VO becomes minus Vs. So since Vs is a negative, VO becomes a positive. The question is asking us to draw the current waveform for resistive load, which if you have learned from the first tutorial, becomes very simple. So the current waveform is exactly the same as voltage waveform for resistive load, but its amplitude will be different, which here is, you see, the amplitude of Vs or VO is Vm, and the amplitude of I becomes Vm over R. And the same thing, if we want to draw the current waveform for highly inductive load, if you remember again from the first tutorial, I told if we have highly inductive load, the current becomes a constant value. So, irrelevant of whatever voltage waveform which we have, the current waveform becomes a DC current if we are doing it for a highly inductive load. 28 volts. So if you want to calculate the RMS voltage, so Vm is the amplitude. If you want to calculate the RMS, will be over root 2. On the other hand, if you want to calculate the average output current, since we have the average output voltage, average output current will become average output voltage over R. This one also I have explained previously in the first tutorial. So, since the question also is given that the resistance is 10 ohm, so the RDC becomes 40 amp. So now, I want to calculate the diode parameter. For diode, I need to calculate from several parameters. First is the peak current. Peak current of the diode is how much? You need to see the waveform. This is my, if I have the, okay, from now we are doing everything for resistive load. The question is, the remaining part of the question is for resistive load. Now, you see that the resistive load, the current is this half cycle like this. How much is the amplitude of this current? Is Vm over R. So, one parameter of diode is its amplitude or maximum current, which here we can see is according to the figure is Vm over R. So, we become 62 ampere. Average current of the diode. From last week, if you remember, last week I had 2 diodes, but now I have 4 diodes. It's the same. I have calculated the average of the output current of I0. But I know that in half of the whole cycle, the current is flowing through D1 and D2 from here to here, 0 to pi. And in the second half of the duty cycle, the current flows in D3 and D4. So if I want to calculate the average current for each diode, since each diode is conducting in half of the whole duty cycle, so the average of each diode current becomes the IDC or IODC over